Right. So log base A, no matter what base it is, if it's log base A of 1, then the answer is 0 for that. That's one of the replacements that you can make. So easy thing to do there. And then the second one, log base A of A is equal to 1. So if the base is the same as what you're taking the log of, it's equal to 1. That's a simplifying property that you can use. Property number 3. Not that you need to know these by number or anything like that. I'm just numbering them. So make sure I get them all. A is the base and then an exponent of a log base A. And do of M. What happens is the log base A and the base A cancel out and it becomes M. That's how that property works. Is the base A and the log base A cancel out in the same way that this log base A cancels that A to make a 1. It's the same kind of idea there. The fourth property, log base A and then the base of an A with an R exponent. What happens with this one? Same thing. This log base A cancels that A, and what's left is the exponent R. And that's how that property can simplify an expression. And a lot of times, if you can simplify it, it makes the equation that we're going to end up solving later on easier to do. That's what we're after here. Fifth one is the product rule. This one doesn't matter what base we're using log base A on all these. It doesn't matter what base it is. It could be base 2, base 5. It doesn't matter. The property still works the same way. The product property says you're taking two things and multiplying them together inside of a log. You can rewrite that as a sum. With the same log on them. So we can either split it apart into a sum, or we could condense it down into a product. And we'll go both directions when we're doing examples here. So multiplication, and the way I always remember this is I remember logarithms are exponents. That's what they are. So if a logarithm is an exponent, when you multiply things that have the same base, like x squared times x to the third, you get x to the fifth because you add exponents. So multiplication inside of a log is like adding exponents. That's the way I've always remembered that. So maybe that's a helpful way. Maybe not. On base A, let's do division, the quotient property. For dividing, what's the rule for exponents when you divide? Subtract. With the logs, top minus bottom. The same log base, and then it's the top minus the bottom. So you can turn a division problem into a subtraction problem, or turn a subtraction problem back into a division problem to make the equation more easily solved. Pop over here to the bottom. Log base A, again, base doesn't matter. And then this one's kind of similar to number 4, except for instead of having the same base, we got a different base. And what that can do is allow you to bring that exponent down to the front. That it would be R times the log base A of M. So you can bring an exponent out to the front. And sometimes that can make the problem much easier to solve, or taking the number from the front back into an exponent can make the problem easier to solve. A lot of different things that can happen there. E to the x natural log of A is actually A to the x. Weird one that doesn't get used very often at all, but it is one of the properties that our textbook tends to, they throw it in there maybe once in every 100 problems. So it's not very often used. I would feel pretty confident in saying you won't see that property on the test, Canvas quiz, or final. But it is a property that's in your textbook that we try to cover. Natural log of E. This one is kind of used. It's just a simplifying property that the natural log of e is 1. Remember, a natural log is log base e. They're the same thing. So that's canceling out. It's the same. It really is the same property as number 2 was, except for it's a natural log instead of log base something else. All right. So got all those properties. We're going to practice using them a little bit as we go here and try to write the log as a sum or difference. And you may hear me say expand. Expand the logarithm. But writing it as a sum or difference. So what we want to do here is take anything that we've got and split it apart. If it's multiplied, we're going to turn it into addition. If it's divided, we're going to turn it into subtraction. And do some things there with our exponents and make them work. So let's start with example A. We'll do log base 4 of parentheses x and then a square root of x squared plus 1. All right. So when I look at this problem, I see a few things happening. The first big thing is seeing that we've got a log, and then inside of that log, we got x times the square root stuff. So that's a multiplication. So when I see that multiplication, I go ahead and say, oh, well, I know I can turn any multiplication problem that's inside of a log into an addition problem. And that looks pretty good, but it's not done yet, because then I need to look at each individual piece there. Well, x, it's plain. It really doesn't have anything else going on. So there's nothing else I can do to this piece. But this next piece, I've got a square root in there, and we've got to remember that a square root is actually an exponent. That this is log base 4 of x plus log base 4 of x squared plus 1 to the 1/2 power. That a square root is the 1/2 exponent. A cubed root is the 1/3 exponent. A fourth root is a 1/4 exponent. That's the reciprocal. Square root is 1/2. And so here we have a log of something with an exponent on it. So I look at my properties there, and I see this one right here that allows me to take that exponent and drop it down to the front for that particular log. So I'm using that 7 property there, and I'm going to rewrite that as log base 4 of x plus, and then I'm going to pull that 1/2 down here to the front. 1/2 log base 4 of x squared plus 1. I don't have any properties of logs that let me split up an addition problem. I only have properties of logs that let me split up multiplication or division problems or exponents. So once I get there, that's all I can do to this problem, and that's expanded as far as it will. There's nothing else that you could do to that problem. Okay. All right, let's look at another. Natural log x squared over x minus 1 cubed. The biggest piece of advice I could give you with this is don't try to do too much at once, and that's where you usually get confused, is if you try to do too much at once. Just take it one step at a time. What's the big thing in this problem? The most obvious piece of math. It's division. It's a big fraction. Anytime you see a big fraction, you know it's division. Division in logs turns into what? Subtraction. So we got natural log of the top minus natural log of the bottom. Then I see those pieces and I try to simplify each piece. So I look at this first one. I got an exponent here. So what can I do with that exponent? Bring it to the front. Yeah, just like we did on that last problem. So 2 natural log of x Can I do that on the second one with this 3? Is it an exponent? Yeah. So I can take that 3 and pull it down to the front. I don't have any log properties that let me break up a subtraction problem. So I can't do anything else with that. This is natural log of x. There's nothing else to do there. So that is as far as that one will expand. Let's go to maybe a little bit more difficult problem. Got a lot more going on in it anyway. And we're going to rewrite this as a sum or a difference, maybe a little bit of both. What's the biggest thing we see in the problem? It's division. So that's going to turn into subtraction. And I see that square root up top. I'm going to go ahead and write that as x squared plus 1 to the 1/2 power. Most of the time, that's what you're going to want to do. There are very few times that you won't do that. And then it's going to be minus log base 5 of x cubed x plus 1 to the 4th. Okay. So one step at a time. What can I do to this first piece, the log base 5 of x squared plus 1 to the 1/2 power? Throw the 1/2 to the front. That's right. Can I do anything else with this x squared plus 1? No, because I don't have any properties that work with addition inside of a log. Only multiplication and division and exponents. Okay? So I've done everything I can to the first piece. Now let's look at the second piece. What's going on here? I can't because they don't have the same base. One's got an x as a base, the other one has x plus 1 as a base. So we can't put them together. But that makes it even more complicated if we do that. It legally, mathematically, that's legal, but it wouldn't make it easier to split apart. The idea we're looking at here is we got what's going on between, and let's play off of that. You said distributed property, which uses what math operation? Multiplying. So really, we're multiplying x to the 3rd times this. So that's a multiplication problem, which can be split apart as adding, right? Multiplication can be turned into addition. Here's the trick on this one, is because it's subtraction of all of that, we need to think about it as log base 5 of x cubed plus log base 5 x plus 1 to the 4th, like in brackets or parentheses there. I'm using brackets, parentheses would have worked as well. But it's a subtraction of all of that. And then what else could I do to this stuff that's in the brackets? Yeah, move the exponents to the front of each of those pieces. So I've got 3 log base 5 of x plus 4 log base 5 of x plus 1. That's okay. That's correct. What could I do with the minus sign, though, and get rid of the brackets? Now, in this case, it can be treated like distributed property, that I could distribute that negative to each one. And this would be correct. The blue one is also correct. But this one, the one with the negative sign distributed to both of them, is the most like what you're going to see on final exam or a test or something like that. that negative all distributed. And here's a thing that can help you there. If it's in the bottom in the fraction of the original problem, it should have a minus sign in front of it. If it's in the top, it should be a positive term out of that. That's what you can always look for. Expanding is a good way to learn the properties. The real work that you're going to probably use the most often in doing this stuff, and when we get to solve an equation, is condensing. Okay, condense into a single log, or rewrite as a single logarithm. The instructions could be either of those. So what you're starting with is something that's in its expanded form, like log base 3 of 7 plus 4 log base 3 of x. So when you look at those, you try to look, okay, which one's the most complicated or has the most stuff going on out of that? And obviously the second one does. What can you do to undo something that expanded this? Yeah, this 4 goes back up top to make x to the 4th. So if I write out extra steps here, and after you've done a few of these, you'll quit doing that, and you'll just say, okay, I'm going to try to do it all at once. So that becomes x to the 4th, and then the addition between them says you're doing what with the two pieces? You're multiplying. So the final answer would be log base 3 of 7 x to the 4th. And there you've condensed it into one single log out of that using those properties. And this is more like what you'll be doing to solve an equation in the next few sections. Let's do another one. 2/3 natural log of x minus natural log of x squared minus 1. We want to condense that into a single log. Okay, so this is going to turn into natural log of x to the 2/3. Now what? It's dividing because it's subtraction, right? Subtraction turns into division. So we're going to have natural log. What goes on top? Yeah, the one that's in front goes on top. And on the bottom, we got x squared minus 1. This is correct, but you may also see it written the cube root of x squared on top. This is also correct. Both of those are equally correct and equally likely to be seen on the final or the exam or on Canvas quiz. Because it's just taking that notation and changing it. 2/3 power is a cube root, and then the numerator of the fraction is on the inside. All right. There's condensing a couple. Let's do this one. A little bit more going on this one. So we had 3 log base 5 of x plus log base 5 of 6 plus log base 5 of x squared plus 1 minus log base 5 of x minus 3. What do we do now? What does the addition between them do? All right, so anything with addition between it is going to be multiplied together. And then if there's a subtraction between them, what does that do? Divide. So what's the only part we're going to divide by here? It's the end. This piece right here is the only one that gets divided by. The rest of them are multiplied together. So if we can condense these three, and then we just know we got to divide by that last one. Okay. So what does log base 5 of x, or 3 log base 5 of x turn into? Yeah, so this becomes x to the third. And then 6 and that x to the third do what? They multiply. So we really have log base 5 of 6x to the third times x squared plus 1. What does this part do? You divide by that. And there you have a condensed logarithm. 6x to the third, and then x squared plus 1, and then an x minus 3 in the denominator. Nothing else really to do there. No. You're trying to, any of the problems where they're asking you to condense to one log, the bases will have to be the same. Good question. But yeah, the bases will have to be the same. Let's do one more of these, and then we'll get into the next thing. Example G, 3 log of x plus 2 log of x plus 5 minus log of 12 minus 3 log x minus 2. What log base is this? 10. It doesn't matter, but it's good to know that we know there's log base 10. All right. Yikes. There's two things with a minus sign on it in this one. What's the only thing that means? Divide by how many things? 2 things. That's what it means. Don't overthink it. That's all it means. So that means that this stuff is added together, so it's going to be doing what? Multiplying. So what does it turn into? X cubed and then x plus 5 squared. This 2 goes up here, this 3 goes up there. That's where we're getting that part. And then in the denominator of that fraction, what goes in the denominator of that? 12. And then what does the last piece condense to be? X minus 2 cubed. Does this 3 goes back up there? And there we've rewritten that as 1 log in one step, really. Positive pieces are on top. Negative pieces are going to be what you divided by. If there's a minus sign in front of that stuff, you know it's going to go to the denominator. It really doesn't get much more complicated than that. Okay. All right. So let's look at solving some logarithmic equations and exponential equations. So we're going to see a little bit of repeat of some things we did last week, and then some things where we're going to use a little bit of these properties to help us get there. Okay, so one new page. 6 solving logarithmic and exponential equations. Logarithmic equations have logs in them. Exponential equations don't. So let's just start with an example. 2 log base 5 of x equals log base 5 of 9. Obviously, this is a logarithmic equation because it has logs in it. And it takes a little bit of our property knowledge to get this to where we can solve it. Because at the current juncture, the log bases are the same. We would normally be able to drop those, but that 2 in the front is a problem. How do we move that 2? Yeah, it becomes x squared. So it's log base 5 x squared equals log base 5 of 9. Now, here is the math that makes those logs disappear. To solve a logarithmic equation, you're going to do what's called exponentiate. And to exponentiate the right way, you look at the base of the log. The base of the log is 5. So you're going to exponentiate with a 5 as the base. So what you do is you say 5 raised to that power. And one of our log properties back from section 5, going back all the way here, anytime we have that going on in property 3, the logs cancel out. All that's left is the exponent, or is left is what was inside of the log. So for our problem, this log base 5 and that 5 cancel out. This log base 5 and that 5 cancels out. We're left with x squared equals 9, and we try to solve that. Yes, ma'am. Yes. Yeah, whatever the base of the log is, that's what you use as the base for your exponentiation. Yes, sir. That's exactly what they're canceling each other out. That's what's happening. Yeah, they're disappearing. Where it changes is when there's not a log on the other side and you've got some other number there. And we're going to see that as we get into further problems here. So how do we solve this? Square root. So I take the square root of x squared and the square root of 9. If I take the square root of 9, what do I have to remember? Plus or minus. Okay, so what's the square root of 9? Plus or minus 3. So we got two answers. X equals 3, x equals -3. Now, what we have to do anytime we get more than one answer, or anytime we get any answer on this stuff, we need to check those inside the original problem. What's the only kind of number we cannot take the log of? Talked about this a little bit last week. Has to deal with the domain of a logarithmic function. That it's always positive. So we can't take the log of 0 or any negative numbers. So this one right here, if I plug that back into the original problem, that would be the log base 5 of a negative number. And that's not possible to do. So you know that we're going to throw that answer out. And x equals 3 is the only answer. So -3 is what's called an extraneous solution, meaning it's extra and it doesn't work in the original problem. Most of the time, you will throw out the negative answer, but not all the time. So by it not being all the time, that means you got to check it every time. Okay, so always check your answers. Go back to the original problem where the logs were at and plug them in. If it turns out to be a negative inside of that log, you know that's not going to work. So that's how you throw that. But always check it when you go back. Okay. All right, let's look at another one. Maybe it's a little bit more our level. Let's do log base 5 again. And let's use x plus 6 plus log base 5 of x plus 2. And all that is equal to 1. I've got two logs on the same side. They're the same base. They're tied together with addition. How could I combine them? Multiplication. So this is really log base 5 of x plus 6 times x plus 2 equals 1. And we could multiply that out. We will in a minute. But let's get rid of the log first. What do I do to get rid of a log base 5? Exponentiate. Yeah, that's the word. It's a tough word. Exponentiate with what? What number? 5. So 5 is the base on both sides. So on this side, 5 as the base cancels out the log base 5. They go away. On the other side, we have 5 to the first power, which is a number. What is 5 to the first power? 5. So we really have this problem to work out. X plus 6 times x plus 2 is equal to 5. And we need to solve that. Well, I know that if I multiply those two together, I'm going to get an x squared. So I've got a quadratic going on. So I've got to work it like a quadratic. So let's go ahead and multiply that out. So that'd be x squared plus 2x plus 6x is plus 8x plus 12 is equal to 5. If I'm going to solve a quadratic, what does it need to be equal to? 0. So move that 5 over. X squared plus 8x plus 7 equals 0. I've got a quadratic equal to 0. What are my options for solving that? Factoring, square roots, quadratic formula. Any of the, I don't think square roots is not an option on this one because the 8x in the middle. If it were just x squared and 7, yeah, perfectly good option. But the 8x in the middle messes that up unless you want to do completing the square, which nobody ever wants to do that because it takes forever. So either factoring it with the x method thing or quadratic formula. I'm going to factor this one because I do know what multiplies to be 7 and adds to be 8. 7 and 1. So my factors are x plus 7, x plus 1. And I solve those by setting them equal to 0. And I get 2 of the answers that are negative. And I just said we normally throw out the negative answer, but both of them are negative in this case. Again, you can't just go by that. You've got to check them in the original. So if I check the negative 7 in the original problem, and I plug that in here, negative 7 plus 6, negative 7 plus 2. What's negative 7 plus 6? Negative 1. Can we take the log of a negative number? No. So that means right there, that's enough. I don't even have to do the other part. That right there is enough information to say this one's out. Does that mean that negative 1 is in? Not necessarily. We got to check it too. Because it could have no solution. And we've got to check to make sure it's not extraneous as well. So if I plug that in, negative 1 plus 6, that's 5. So that works in that one. So I'm going to go over here, negative 1 plus 2. That's positive 1. That's doable. That works. So negative 1 does work, and we are going to keep it. So that's the one that we checked, and we know it works. The other one is an extraneous solution, so we throw it away. Plug it back in for x in the original problem, and make sure the logs are not negative, that we're not taking the log of a negative number or 0. If it is a 0 or a negative number, you know that answer's out. All right. Here's a fun one. I love that when a math teacher says that. Here's a fun one. Natural log of x plus natural log of x minus 4 equals natural log x plus 6. What in the world? Well, the left side's got 2 pieces. The right side has 1. They all have the same log. So they should. For us to be able to work them, they need to. They're not going to throw any at you that don't. How could we condense that left side into 1 log? Multiplication. So it's natural log of x minus 4. And this other side's natural log of x plus 6. Now the logs are the same. What do I do to get rid of a natural log? Remember, natural log is log base what? E. So I'm going to, E is a number. Guys, don't forget that. E is just a number. So I'm going to exponentiate with an E. Works great here because what does E do to the natural log? They cancel each other out. Gets rid of it. So I've got x squared minus 4x equals x plus 6. So I just did that distributive property there because I'm going to have to anyway. It's quadratic because I got x squared. So that means I need to get it equal to 0. So I would move the x and move the 6 That's x squared minus x. That it would be minus 4x. Thank you. So that'd be minus 5x. I don't know why things aren't working out the way they should. But other way, I'm going to factor. And there's equal to 0. You could factor that. This one does factor. Multiply to be negative 6, add to be negative 5. Be negative 6 and 1. So x minus 6, x plus 1. And then set each of those equal to 0. X equals 6. And x equals negative 1. You would think you're going to throw out the negative 1. You're not sure, but just check it to make sure. If I go back to the original problem, the very first term has natural log of x. If I throw a negative 1 right there, it automatically says, I can't do it. Not going to work. So this one's out. Let's make sure 6 doesn't give us a negative somewhere else. So if I plug 6 in, it's okay in the first piece. 6 minus 4 is positive 2, so that's okay. 6 plus 6 is positive 12, so that's okay. So it checks out. So 6 is the one that works. We'll keep it. There will be problems where you'll keep both of them. And there could be problems where you throw both of them out. It happens. So these are logarithmic problems. They had logs in them to begin with. We used exponentiation to solve them. So let's look at some exponential problems, and we'll use logarithms to solve them. 2 to the x equals 5. Now, last week we had problems like 2 to the x equals 8. And we were able to change that 8 into 2 to the third. And we knew that x would equal 3. But that's not, 5 doesn't work that way, right? You can't say 2 to some, nice, easy power gets you 5. 2 squared is 4. 2 to the third is 8. So we're somewhere between 2 and 3 should be our answer, but what number is it? Who knows? So we've got to look at trying to solve that. So once we get a base like this, we can use a logarithm with that same base to get rid of it. That I can take the log base 2 of both sides. Whatever the base is, where your variable is in the exponent, use that log base. So if it's log base 2, you're going to use, or if it's 2 to a power, you're going to use a log base 2. If it were 3 to the x, you'd use a log base 3. If it was 5 to the 4x, you'd use a log base 5. Whatever the base is, that's going to be what log base you're going to use. Okay? That's how that can cancel out. Okay, and then this right here, one of our properties from 6.5 says, oh, that cancels out to give you x. It's just log base 2 of 5, because that doesn't simplify any. That's the exact answer. The decimal approximation for that, you can use our calculator to find. So to get it to do log base 2 of 5, hit the math button. Press the up arrow. Do we get log base? And then we can put the 2 there and the 5 there. And we're going to go 3 decimal places. That's common practice for this, is 3 decimal places. So that'd be 2.322. Yes, if you got, I'm about to show you, if you got an 83, how to get that to do. You got to use a change base formula and divide with division. You got to do a log on the top and a log on the bottom. I'll show you in just a second. For everybody else, and that way it's on the video too. So 2.322. That's the decimal approximation. If you've got an 84, or if you'd rather not use the log base, you can do log base 2 or log, just regular log button of 5, close the parentheses, divided by log of the base. You get the exact same number. Sometimes that's quicker to do it that way. And so just using the regular log button over on the left, the big number is on top, the base is in the bottom. The base is in the bottom is always what how I remember to do it that way. And that will get you the same answer as the log base function on the 84 plus, or one of the newer colored ones does. All right. Let's do another example E. 8 times 3 to the x equals 5. This is a fun one. It's got fractions in it. You're saying, no, it doesn't. There's not a fraction 1 in there. Yeah, there is. Eventually. What part has the exponent with the variable? Well, which part of that first part? The 8 or the 3? The 3. So the 8's in the way. Let's get rid of it. How do we get rid of it? Divide. Because it's multiplying. So if I divide by 8, oh, now there's a fraction. Just 5/8. 0.625, I think. Something like that. 6.6125, maybe. Used to have those memorized. I don't have them memorized anymore. Don't use them anymore. All right, so now we've got something with an exponent, with a variable in the exponent, and we've got a base on that side. What log base should we use to get rid of that? 3. So I'm going to use log base 3 on both sides. Log base 3 of 3 to the x. And I'm writing an extra step here. Log base 3 of 5/8. This side, log base 3 cancels 3, there's x. Hey, wow, I'm done. That's my answer. I just need to get a decimal approximation for that as well. So you can do it this way. Log of 5/8 divided by log of 3. Negative 0.42. We go to 3 decimal places again. So 0.428. Or if you did the log base trick. Log base 3 of 5/8. The same number. Negative 0.428. Not too difficult. Yet. All right. So I kind of told you a little bit of a fib earlier when you asked about would you have different bases on the logs. On the logs you won't, but on the exponential equations you could. Okay, so we're going to look at a problem that has a different base on the exponential equation. So but it's actually, to me, it makes it easier because you don't have to think about what log to use. You always use the natural log. That's just, to me, makes it easier. So let's start with this one. 5 to the x minus 2. So we got a base of a 5. And we're thinking, oh, I probably could use log base 5 here to solve this. But then on the other side, they were really mean and put a 3 as the base and then 3x plus 2 as the exponent. And that's just mean. Because the bases aren't the same. If the bases were both 5s, this is a super easy problem that I would think probably my Algebra 1 kids could do at school. But it's not. It's much more difficult than that because the bases are not the same. So what you can do is use a natural log of each side. Anytime the bases aren't the same, you got a variable exponent on both sides, you're going to use a natural log of each side. Oops, that's minus 2. Yes. Has to be a variable exponent. If there's not a variable in the exponent on the right-hand side, you just work it out and get a number, and then you can go back to using log base 5. But so here we got natural log of 3 to the 3x plus 2. Now here's the thing that happens is the properties of logs. This exponent comes down to the front. This exponent comes down to the front. So we have x minus 2 times the natural log of 5. And then on this side we have 3x plus 2 times the natural log of 3. What you've got to remember here is that the natural log of 5 is just a number. It's an ugly decimal number. That's why we're not writing out the decimal equivalent to it. It's this long. Same thing with natural log of 3. It's just a number. It's like the number 6 there. It's just a number. But this is a especially long decimal number. So we're using this notation for it instead of its decimal equivalent. Okay? Now, it's not as clean as some of the others we had because of the natural log there, and because we've got the x minus 2 involved, and here with the 3x plus 2 involved. What can happen here and can make it a little bit easier to do is getting all the x things together and the things without x together. Because when you're solving an equation, isn't that what you're trying to do? You get x by itself. So you need everything that's not an x to go to the other side. So in order to do that, you've got to take this and say, oh, that's just a number. And really, that's distributive property. That I'm distributing x times the natural log of 5 minus 2 times the natural log of 5. Same thing over here. But that's 3x natural log of 3 plus 2 natural log of 3. Because it was x minus 2 in the exponent. So when I distribute it, that's a negative. It's like a negative 2, a minus 2, a negative 2. And now we've got pieces that have x, and then we've got pieces that don't have x. We need to get the x pieces to one side, the non-x pieces to the other side. That's our job. That's what solving an equation does. Those are not really pretty numbers that are in there, but they're just numbers. So let's work from there. So I'm going to move the 2 natural log of 5 by addition. That'll cancel it out there. So that's x natural log of 5 equals 3x natural log of 3 plus 2 natural log of 3 plus 2 natural log of 5. I can't combine these two pieces because they're different. One's a natural log of 3, one's a natural log of 5. They don't combine to be natural log of 8. That's not how that works. But they are just numbers. That's all you got to remember. They're numbers. They just look weird. Okay? And then I need to get this thing over to the other side. So how do I move it? Yeah, good job. Subtraction. That's the right one because it's a positive 3x natural log of 3. So I'm going to subtract it. There, it's gone from that side. So here I have x natural log of 5 minus 3x natural log of 3 equals 2 natural log of 3, 2 natural log of 5. What do these two pieces over here share? Well, the natural log is the same, but the factor that they share that's the same is the x. And I could pull that x out by factoring x parentheses natural log of 5 minus 3 natural log of 3. And then the other side stays the same. Haven't done anything to it. So I took what they had in common, the x, pulled it out to the front. So now it's x times, what is this, essentially? Stuff in parentheses. Natural log of 5 minus 3 natural log of 3. What are those pieces individually? Say it louder. They're numbers. So this is like 7 times x. That's all this really is. It's an ugly decimal number, but it's times x. So how do we get rid of a number when it's multiplied times x? Like if we were going to have it, if we had this equation, 7x equals 21. How do we solve that? Divide by the number, right? This stuff over here is just a number. So to get rid of it, I'm going to divide by it. Yeah, it looks like it's just rocket science. It's not. Trust me. Well, Mr. Isbell wouldn't be doing it. Now, this side over here, these cancel out. There's our x. 2 natural log of 3, 2 natural log of 5, over natural log of 5 minus 3 natural log of 3. We're going to get a decimal approximation for that. 2 natural log 3, close parentheses, plus 2 natural log 5. That answer divided by, now we'll put parentheses and do the bottom part. Natural log of 5, parentheses, close them, minus 3 natural log 3. Close the parentheses. Round to 3 decimal places would be negative 3.212. That's as tough as they get. You won't see very many of those. Maybe one over the course of the material. It's not that bad. You just got to keep in mind what parts are just numbers. They look ugly because they got that natural log thrown in there, but they're really just numbers, and you just got to keep that in mind. Hey, this is just a number, and it might help you as you go along. If something is just a number, circle it, and you know, hey, the things that I've circled are just numbers. Maybe that helps you out as you're doing those. If it is blowing your mind a little bit there. Okay, 2 sections down, 3 to go. All right, so we've done the techniques for solving. What we're going to do now is apply that to financial models, like savings accounts and IRAs and things like that. There's some financial formulas that can help you there. And this is section 6.7, financial models. Here's one of our formulas that we'll need to know. All right, I'm point at stuff and tell you what it means. P is the principal. The guy you go see when you're in trouble. No, that's not what that is. It's the initial investment. How much you're putting in your account. What your initial investment is what that is. All right. The N, it's in 2 places. It's the number of times interest compounds. A year. So this is actually, I'm going to label this is the compound interest formula. Compound interest is how most savings accounts work. Very few do continuous interest, but we will talk about continuous interest. None of them do simple interest. But compound interest is how most of this stuff works in the bank. Anybody work at the bank? I usually have 1 or 2 in every class that work at a bank and do that stuff. And of course, a computer does all of it for you now. Nobody ever calculates it by hand. I like to check them every now and then just because I'm nerdy like that. So hadn't caught them cheating me yet. Time in years, that T there is time in years. Always in years. So if they say it's for 30 days, you need to do 30 out of 365 and figure that up as in years. R, which is right here, that's your interest rate. So if it's 1.5%, or as most savings accounts right now are, like 0.5%, or 0.5%. That's what most regular savings accounts are doing right now. Not very good. But your interest rate is there. All right. So what we're going to do is we're going to find out how much the account is worth after a certain amount of time, left alone if you don't make any other deposits or anything like that, what happens to it. And then we're also going to take that as an equation and be able to find how much time it would take for your account to reach a certain amount of money. Say you're trying to save for a car and you put money in this account and you just left it there and hope, let the interest build over time, and you're hoping that happens. So let's look at just a few little scenarios here and just a few scenarios for that. So let's start with something simple and say you had a rich uncle who passed away and he gave you some money, and I always, with my high school kids, I always say, you got money for graduation and you didn't blow it on a senior trip. You actually were smart and put $1,500 in the bank. And for some reason, some bankers giving you 2.5% interest compounded quarterly. And let's say you went to college, and like most people, you probably not going to finish in 4 years. So let's say you're putting this money away and you're going to have it for when you graduate from college and you move to a new city and get your job. So you're leaving it there for 5 years. All right, what's the account worth? All right, so a formula, principal investment, 1 plus R over N, all that to the NT. We're going to plug in the things we know. All right, principal investment, how much money do we throw into that account and leave alone? $1,500. The 1 is always there. What's our interest rate? 2.5%. So let's put that as a decimal. So that'd be 0.025. And the N is how many times it compounds a year. Quarterly means it compounds how many times? 4 times. Semi-annually would be 2 times. Monthly would be 12 times. Weekly would be 52. That sort of thing. Just know those basic things there. And then N is 4 still. T, how long are we leaving it there? 5 years. Okay. We want to see how much is left or how much is in there after 5 years. So this one, we're not solving for anything. We're just finding out how much that's worth. We're doing that math. I'm going to use a calculator to do it. I don't know why I'm doing that math in my head. So 1,500. It'd be impressive if I could, wouldn't it? I'm not impressive. It's okay. Story of my life. Divided by 4. Close the parentheses, and then a little house stop symbol to get into the exponent area. And I usually just go ahead and multiply the 4 times 5. I think I can do that math in my head. That's 20. An exponent of 20. So in 5 years of us doing nothing to that account, just putting that $1,500 in there and forgetting about it, we've made our account worth $1,699.06, round to the nearest cent since we're dealing with money. Almost $1,700. So we gained almost $200 without doing anything. It's nice when you don't do anything. Now, normally we would try to put a little extra money in there over time, and that complicates the compound interest thing because you've got to calculate for a certain amount of time how much was the balance here, and then it goes every time you make a deposit, it starts it over and goes until you make the next deposit. But we're not going to be that complicated with things in this class. You can take a finance class if you don't really do that. I promise they'll let you. Now let's take that idea and let's actually try to use our equation solving skills to figure out how long we should leave $1,500 in the bank so that we have a certain amount at the end. So how long should we leave our $1,500 in an account drawing 1.5% quarterly to have $2,500 at the end. So we're trying to solve this thing for what? T, the time. We got A equals P, 1 plus R over N to the NT. We're trying to solve this equation for time. So the variable in the exponent. So this fits into the section we're talking about here. So we're going to plug in the things we know. We want the account to be worth how much? $2,500. So that's going to be the account worth. That's what A stands for. How much did we throw in the bank? $1,500. That's our principal. And then our rate, 0.15, compounded quarterly, which is 4T. All right. Well, that's weird. Now what? Got to get this guy by himself. So we got this base here. That's a number, by the way. That base is a number. We got this number out here in the front that's doing what to all of this? Multiplying. So how can we get rid of it? If I divide by 1,500, that'll get rid of that. Okay. And the zeros cancel out. That's 5/3. And then that's going to be a nasty decimal number. I'm not even going to mess with finding it. I'm just going to rewrite it. It's easier to rewrite it like this than it is to write out that decimal. I'm fairly certain that 1 plus 0.015 over 4 is not the same as 5/3. Pretty safe saying that. So what I'm saying is the bases are not the same on each side. So if the bases are not the same, what do we use to get the exponent, the variable out of the exponent? The natural log. So we're going to take the natural log of both sides. So LN of both sides. Okay. So natural log of 5/3. And then that allows me to do this, drop that 4T down. So that's 4T, natural log of 1 plus 0.015 over 4. Again, that's just a number. How can I get T by itself? And that other all that other stuff goes with it because it's just a number too. So it's 4 times T times the natural log of that. So to get T by itself, I divide by everything it's not a T, and that would involve all that other stuff. That's a good way of putting it because it's really other stuff there. 4 natural log 1 plus 0.015 over 4. And there's T by itself. And I just need to work that out. And I'm not going to do it by hand, that's for sure. Natural log of 5/3. And I'm going to divide that answer by 4 times the natural log of 1 plus 0.015 divided by 4. Close the parentheses, close the parentheses. 34.12, we'll round up, even though the bank probably won't. 34.12 years. We got to leave that in the bank for 34 years to make $1,000. But we didn't have to do any work to get that $1,000. Okay, this is assuming we're just putting it in that fund and leaving it for 34 years. Okay? So you can see if you had $10,000 and you put that into a fund that earned 1.5% interest, your money would grow a lot faster the bigger that initial investment is. So I always try to pass that knowledge on to my high school kids. You don't know how good you got it. Not every day in your life. People just give you money for walking across the football field and getting a diploma cover. All right, continuous interest. Continuous interest has a similar formula, but it's actually easier. I call it the PERT formula, the old shampoo. I think they still make it. PERT, P times E to the RT. P is still your principal. R is still your rate. And T is still time in years. Nothing fancy about this. What this is the interest is continually being pumped back into the account. Not quarterly. It's every quarter they put the interest in, and then your new balance starts. Continuous, it's over and over and over. It's I don't know if it's per second as far as the computer calculation, but it's continuous always. And, it's not a set date that they add the interest to your account. All right, so with small amounts of money, it doesn't change your account balance very much compared to compound interest. But as the money level increases and the length of time increases, it can make a large difference in how much your investment is worth. So let's look at an example. Let's say we invest $300,000 because we got that kind of money at 2.75% continuously for 6 years. What is the account worth? I always like doing these because I always pretend I won the lottery. Never going to happen, but it's nice to dream. Odds of winning are too low. Got a better chance of going outside and getting struck by lightning. A real good chance of doing that today. Thunderstorm. Yeah, it's pretty low, especially Powerball. Very, very low probability of winning. And plug it in, work it out. That's all you do. Now, to get the E with your calculator, that's what you got to really know here. You got 300,000. One more zero. There we go. And then E, you hit second, and then the natural log button. And that'll put an E, and then it throws an exponent there. No matter what version of the calculator you got, it does that. And then you put in the amount. So 0.0275. Is that what did I even write? Yeah, that's right. And then times how many years? We did 6 years. And tell it to do the work. So after 6 years, $300,000 earns just almost $54,000. Yes, ma'am. No. That that E is e to the first power. What we need is an E that's got a different exponent. So definitely a different. If you're using e to the first power, yes, it's the same. But if it's e to the third, you got to use the one above the Elliott.
Are we going to find 6 just by the exponent?
Yes, yeah, just by the 0.0275. And we get 353,817. Have you got $300,000 there?
Yeah.
0.0275.
Oh no.
That's probably what it is. 353,817. All right. And how many cents we had? 94 cents. Almost $1. Yay! That's a lot of money. I wish I had 300,000 to throw in the bank. All right. If you got here's a kind of a theory type question. How long does it take to double an investment? With the 2.75% interest. Continuously. All right, anytime they start throwing those words out like double, triple, quadruple, you can make your problem so much easier. Because if you're doubling an investment, the account worth is twice the amount you start with. You could pick any amount to start with. You could pick $1 million or $1, and the math will work out the same. Which one's easier to work with, millions or one? One. So your initial investment, anytime they ask you something about doubling an account, continuous interest or compound interest, your initial investment, your P, should be a 1. And your account worth, if you're doubling 1, your account worth is going to be 2. And since this one is continuously, we'll use the PERT formula, E to the RT. But we don't know what T is. Bless you. All right. Technically, you got to divide by that 1. But anything divided by 1, same thing back. What do we do to get rid of the E? A natural log. So the natural log of 2 equals 0.0275 T. How do we get T by itself? Yeah, divided by that 0.275. Remember, natural log of 2 is just a number. Natural log of 2, close the parentheses, divided by 0.0275. 25.21 years. Yes, ma'am, that is correct. Yeah. To cancel out an E, you're going to use the natural log, the LE in there. Yeah. 25.21 years. Same sort of work if they ask you for what interest rate you would need for it to double in 7 years or something like that. You can use that thing. Same principle for using the compound interest. If they ask you to double something and use compound interest quarterly, you'd plug in a 1 for P and a 2 for the account worth, and that would get you that. All right. Now, PowerPoint time. I'm usually not a big PowerPoint user, but this one, it is kind of helpful in getting some things going here. All right, so this section 6.8 is the one I'm using, starting with. So 6.8, they both look the same. So the one that looks like this, they look the same. But this one says 6.8 on the front. 6.8, exponential growth, decay models, Newton's law, and logistic growth and decay models. Okay, so flip it over to the back side of the front page there, and you see that formula written there. This is the exact same thing as the PERT formula. It is no different. It's just got different letters in it. The N of T, that means your population over time. The N sub 0 is how many you started with, like the principal investment is. The K is just like your rate, like the rate of growth. For money, it's the interest rate. For us, for here with bacteria or cells, it's the rate at which they're growing. Okay, so that K is the same thing. So, and you can see that on that slide there. The initial N sub 0 is the initial number of cells. K is the positive constant that represents the growth rate, like an interest rate of the cells. And the T is still time. Time is not in years with this, though. That's the difference. Time is going to be given to you in the problem. What unit it is. If it's days, hours, depending on what you're dealing with, what it changes to. So that's why it's kind of its own separate section. Because the financial stuff, T is always in years. With bacterial growth, not necessarily happening. All right, so next slide, bacterial growth. Colony of bacteria increases according to the law of uninhibited growth. So that means it fits that formula that the previous slide had. That's all that means. Okay. N is number of cells. T is time in hours. So they give us the unit. Time is in hours. And express N as a function of T. If the number of bacteria doubles in 5 hours, find the function that gives the number of cells in the culture. How long will it take for that size of that colony to triple? How long will it take for the population to double a second time? That is, increase 4 times. So here they're asking us to write the initial equation. Then how long does it take for it to triple? How long does it take to quadruple? Is what they're asking for in those different parts. So let's start with the first part. Right, here we go. All right. Initial formula. N sub 0 is how many you got at the beginning. And E is always there. K is your growth rate. T is time. All right. So we need to find the growth rate for this. Okay. So we're N of 5 hours. 2 times, it doubles in 5 hours. So that's going to give us that 2 times N to the 0, okay, at 5 hours. Now, here's the math that's happening there. This is plugging in the stuff, okay? We know that whatever the initial amount was, we'll use a 1. It doubles in 5 hours. So there they're plugging in the 5 for T. The K was what we're trying to find. K is what we're looking for. This line right here, there's an understood 1 in front of that. That's that 1 and 2 thing. Just like we did on that last example from the financial models. This is exactly the same thing. It's just talking about a colony of bacteria instead. So they're skipping a step in between you. What did they do to get rid of the E? Natural log. So that's where this comes from over here. Did the natural log on both sides. So it gets rid of the E. There's 5K equal to the natural log of 2. Get K by itself, divide by 5. Then we get this number, that decimal. That natural log of 2, they're saying 1/5 times that. It's the same thing as natural log of 2 divided by 5. And they get this decimal. Then that gives us a start to writing our formula for this particular colony of bacteria. Okay, so we've got our growth rate right here. This is our initial amount we start with. K is our this should be a T right here, not a K. That should be a T. Let me fix that. Okay. All right, that should be a T. Now, That gets us that function that models the growth process for this particular colony of bacteria. Okay, only good for this particular colony, not for any others. Okay, now the next part asks us to do, when does it triple? So tripling, set up the formula with a 3 on one side, a 1 on the other. That's what this line right there is. See where my cursor's at. 3 on one side, there's a 1 in front of that on the other. Solve it. Natural log of both sides to get rid of the e. That gets you this stuff. And then divide to get t. And you get a time. The key that's going to get you here is that the time is in hours. And that goes back to the original problem. They've got to tell you what time is in. Sometimes time's in hours. Sometimes it's in minutes. Sometimes it'll be in days. I've seen it in the past on the final exam. They'll have the same answer. They might have the 7.925 hours as an answer, and then another answer choice have 7.925 minutes. And if you don't pick the right unit, you got it wrong. So pay attention to your units there. Okay. And then D has a little shortcut to it that if it doubles in 5 hours, it would quadruple in twice that amount of time, which would be 10 hours. But you could work it the same way as you did this, except for instead of a 3, what would you put there to quadruple something? Put a 4 there and then rework the problem. You'd still get the same. You'd get 10 on this one for that. So that is definitely something that could be done easily there. All right. The next slide, looking down through there, so flipping over. The decay, the only difference, guys, is that the k is a negative number on the exponent. That's what decay does. The cells die off at a certain radioactive material. Carbon dating uses decay. If you've ever done anything with carbon dating or taken a geology class, they talk about carbon dating and the decay rate of carbon and all that stuff. So all the work is the same. Your K values just ends up being negative when you do this work. Nothing really exciting about how that works. If you look at an example here, traces of burned wood along with ancient stone tools in an archaeological dig in Chile were found to contain approximately 1.67% of the original amount of carbon-14. So this is carbon dating problem. If the half-life of carbon is 5,730 years, approximately when was the tree cut and burned? And then we can use it to graphing utility to graph the relation for the percentage of carbon remaining and time. So we'll look at that too here. So let's get to the work of the problem. And then there's a C part. Half the carbon remaining. We could use that to get the stuff. Let's go on to the work. Where's the work at? Next slide. All right, we start with our formula. Again, this part over here is just, that's what your account worth is, what the amount is in the bank account is. A sub 0 is how much you started with. E to the KT. K is your decay rate in this case. T is time. Time for us in this one is going to be in years, since they talked about the half-life being at 5,730 years. So we know time is in years. So you could find this, the half-life could help you find the decay rate. Half-life 500 or 5,730 years is the half-life. So you'd set up this problem where it's a half. Instead of doubling it, you're taking half. So it's a 1 in front of here, a half over here. Your time was 5,730 years. You're trying to find K. So half-life is found the same way as doubling something would be. Work is nothing different. The things we did in the financial models are exactly the same work you're doing in this. It's just context is a little different. because you got different things going on there. So working on that out, they get this K value, so you get your function built here. Okay, so take that, and we can work from there. That if we know that we had 1.67% of the carbon was remained out of the original amount, here we have that as a decimal, and we're doing this like it's like the half-life problem again. Taking what's that percentage, we're going to try to find how much time that was in years. They're saying it's 33,860 years ago. So you can take that for what you believe about carbon dating. I don't know how accurate it is. It's pretty close on a lot of things, but it gets a little far off sometimes. Now, the graphing utility thing is just typing that equation into the graphing calculator and using X instead of T and looking at the graph, and then you can find things if you need to. I don't think it really helps you much there. All right. Now, next set of problems. Cooling, Newton's law of cooling. All right, Newton's law, you got a lot of things going on here. T is the constant temperature of the surrounding medium. So that means the room temperature, or if they're dropped off in a pot of water, it's the temperature of the water. It's the constant temperature of the surrounding medium. If you're talking about how long has a person been dead, Newton's law of cooling is how they can figure that out. They get the core temperature of the person, the temperature of the room that they were in, and then work out the math and try to find out how long they've been dead to get a time of death on that. Kind of a morbid example, but it's a good example for what this is, what you use it for. And U sub 0 is the initial temperature of the object. So if it was a person, the initial temperature is usually 98.6 is their core temperature normally. But if you had like a piece of metal that you heated to 300 degrees and then laid it down on the floor and then came back 30 minutes later and measured what its temperature was, the initial temperature would be the 300 degrees ideal there. K is always going to be less than 0, which means it's a negative number because it's Newton's law of cooling. Cooling, temperature goes down, right? So the negative K value, negative rate. All right. Now, next. So always interesting that they heat an object to 100 degrees Celsius. That's easy to do. You boil some water, you throw the object in it. Magically, it's 100 degrees Celsius because that's the boiling point of water. So it's really easy to heat an object to that temperature. And then it's allowed to cool in a room whose air temperature is 30 degrees. So that's the medium, the temperature of the medium. That's T. Okay. The initial temperature is 100 degrees. Okay. If the temperature of the object is 80 degrees after 5 minutes, when will its temperature get to 50 degrees? And then awesome stuff with graphing calculator. My thing is the equations. Okay, so let's look at that. Plugging in all that information into that formula that's on that slide. You got your room temperature, how hot the object is. There's your room temperature again. And then E to the KT. We don't know that stuff yet. Okay? Then you got to find K. So the first thing you got to do is find K. So you got to have some information there. It says that after 5 minutes, 5 hours, 5 minutes, it was 80 degrees. So we have a time, we have a temperature. So that allows us to set up this equation 80 plus or equals 30 plus what's 100 minus 30, 70, e to the k times 5. 5 is the minutes. We plugged all that stuff in and they simplified it. They're just solving this equation for k. Same way we were doing in section 6.6 and 6.5, solving those, or 6.6. Getting the e to the something k by itself and then taking a natural log. That's all they're doing there. Nothing really complicated about it. And then once you've done that, you got this. This is your cooling coefficient is what it's called in a science class. It's not a science class, but that's what you'd call that. So if it was a certain kind of metal, that kind of metal has the same cooling coefficient no matter where you're at in the world. But if you raise it to 100 degrees Celsius and leave it in a room that's 30 degrees, the same cooling coefficient happens to it as if you left it in a room that was 15 degrees. It's the same, but that's based on the actual piece of metal that it is. But you found the K value, and then you plugged it in, and there's your formula. You could take that and find the temperature after any amount of time. Or you could replace this side with the temperature you want it to be. So it's like you made your coffee this morning, your Keurig puts it out at 95 degrees Fahrenheit. You want to drink it at an optimum temperature of 80 degrees Fahrenheit. It's not too hot, not too cold. So you could actually find out how long it took using the Newton's law of cooling to do that. Step by step, it's the same things we've done. It's solving equations. There's nothing to it there. And it's the same problem. All right. Logistic model. The logistic model is not used a ton. I don't think I've ever seen it on the final. So I'm just going to mention it. And we'll do a little bit with it in the last section because the calculator can find the logistic equation really, really easily. But the logistic model looks something like this, where you've got a carrying capacity for the, for whatever population you're dealing with. If you're talking about fruit flies, there's a carrying capacity. There's only a certain amount that can survive in a certain environment, and there's a carrying capacity for that. And then you've got A, it's just a number. A, B, C are all just numbers involved. Growth, B is a positive number. Decay, B is a negative number. All that. But the logistic model looks like this. Like I said, I've not seen this on the final very much at all. I don't remember in 8 years of teaching it. I don't think not 8 years, 6 years of teaching I've ever seen it on the final. But anyway, properties of that, you can read those. They're not, overly important as far as that goes. Here's a logistic growth model. In a logistic growth model, questions about this, they're going to hand you this equation and say, here it is. And then they're going to ask you, state the carrying capacity of the growth rate and the growth rate. The carrying capacity, 750, the top number. That's your carrying capacity. Your growth rate, right there. Determine the initial population. The initial population is where time is 0. So you plug a 0 in for t and just crank out that number. Okay. Population after 5 hours. Where do you put the 5? T. Work it out. How long does it take the population to reach 250? Where's 250 go? Over here in the place of that. And then you solve that equation by just multiplying by this down here, and then dividing by subtracting and then dividing. But solving for the variable t out of that. Not nothing fancy about that, but they're going to give you that equation to do that. The last part is the part that's a little tougher, because to solve this you have to multiply and then you can divide by 250 over here and get that number, and then get e to the power by itself. And then once you want to get rid of e, what do you use? Natural log gets rid of e there, and then you can get that number really easily. So in 6.86 hours, we could reach 250 grams of whatever we were dealing with. Okay. Now let's look at 6.9 real quickly and talk about finding a fit, exponential fit, and then logarithmic and logistic. So we're going to build this from data. We use the graphing calculator to help us do that. So this is what we need to do. We need to take this table. So I'm in the 6.9 set of notes. So flip over to the back of the first page. That table that's there, we need to put it into our calculator as list 1 and list 2. Okay. So, graphing calculator. I'm on the home screen. I'm going to hit Stat and then Edit. And I want to clear out list 1. So I'll press Up, Clear, Enter. And that'll empty that list. And I'm going to clear out list 2 the same way. Clear, Enter. And then in list 1, I'm going to put the X values, the years that they gave me there. So 0, 1, up to 6. And then over in list 2, I'm going to put those numbers for the account value. 20,000, 21, 516, 23, 355, 24, 885, 27, 484, 30, 053, and then 32, 622. All right, once I put that in there, I can draw a scatter diagram of that or scatter plot with my graphing calculator by pressing second y equals. It goes to our stat plots. On stat plot 1, just hit enter and then make sure it's selected to be on. The type should be the first option. That's the scatter plot option. L1 should be your X list. L2 should be your Y list. And then it doesn't matter what mark you pick. You can pick any of those you want to. I'm just going to stick with the first one, the little box. If for some reason your X list is not L1 or not L2 for Y list, to get it to change, you hit second and then number 1 to make that L1, and then second, number 2 to make that L2. That's what they should be. Okay. If you got the 83, then you don't have to tell it anything. It'll automatically have those set. It defaults to those. It doesn't have as many options as the 84 does. Once you've done that, hit Graph, and then I'm going to hit Zoom Stat. Zoom. That finishes graph in here. Zoom 9, and it shows me those numbers. Now that it's a little tough to tell that that's exponential. It looks almost linear, but considering we know the subject matter we're dealing with here, that looked like money. The table told us that it was an account value, so normally money is not a linear growth type system. It's an exponential growth system, and there's a little curve to that, not exactly straight. So they're also going to ask you for an exponential thing. So we can see that there's a little bit of an exponential curve to that. It's growing not at a steady rate. It kind of increases a little bit more as it goes to the right. All right. Now, the next thing we want to do is create the exponential function from that. So to do that, we're going to hit the Stat button. We're going to go over to Calc. And we want to do exponential regression. So we're going to look for EXP REG, exponential regression. So it's down at the 0 position, the 10th one in the list. You hit enter. If you're using an 83, it's going to default to these things. List 1 is X, list 2 is Y, and no frequency list. That's what you won't have to do anything. With the 84, you just make sure it's got those things there. If it doesn't, put them there. Leave frequency list blank. Don't worry about storing the regression equation. We're just going to write it down is what we're trying to do. So we'll hit calculate. If you're using 83, just hit enter. And it will find that equation for us that's in this form. A is like your initial amount. B is the the base there, and the x is the exponent. So x is always just going to be x. It's going to tell you the value for a, and then the b is your rate of growth there for that account. So we could round that to, let's see, let's do maybe 3 decimal or 4 decimal places would be a good place to stop there with the b value. But you get those values and you get this equation that's written there on, which slide is it there? Yeah, right there at the bottom of that page on the slide there. They've got the equation written on that slide right there. And I'll go back to the PowerPoint so you can see that. Right there. That equation right there is the same one that we got in our calculator. Those same numbers. 19,820.43 cents. And then well, they did 5 decimal places there instead of 4. That's okay. You'll see which ones to do based on the answers there. So exponential equation, you're going to use EXP, REG. For logarithmic, if they ask for a logarithmic stat, go over to calc. We're going to use the natural log regression, LN, logarithmic, log base E, natural log regression. And you do the same things. You put your table in as list 1 and list 2, and then you use this to get your equation. And this is not a natural log regression, but I'll show you what it's going to look like. It wouldn't do it. I was afraid of that because it's not the right kind of data to do that with. But it'll tell you, it'll show you the equation there that you've got natural log of, if you look on slide, where's that? The next page, logarithmic function. You've got a table of data you could put in. We won't go through all the handle or putting that in. And you could do a scatter plot. But if you look at the middle slide on page 5, there's what the equation generator will look up like for you there. There's a box there that's the picture of the screen from the calculator. It's exactly what it's going to look like there. And then you can also do that with a logistic model. Again, you have your you flip over to page 7 of the last page of the PowerPoint handout there, and you see that there's a logistic model. There's a data table on the previous page that you put in your calculator. You hit stat, go over to calc. You're looking for the logistic model, put that in. It's going to tell you to do all those things, and it may not do this one either because it's not the right kind of data. It's trying. I don't think it'll work because the data's the wrong kind. Okay, but it's going to crank out that same looking picture that you've got there. So really calculator-driven thing to do there to find that out. But very, very easy thing. You'll have a Canvas quiz that'll be up hopefully tonight. If not, it'll be up in the morning. And then we got our Chapter 6 test next Monday night or Monday afternoon, 4 o'clock. And we'll go from there. All right. Appreciate you guys being here today. Y'all be safe going on. It's raining a good bit out there.